process capability analysis, and Module 1 is an overview of what capability analysis is all about. So the topics that are going to be covered in this particular module, I'm going to talk about the concept of what process capability analysis is. We're going to look at examples regarding both good and poor processes when we're looking at them in relation to their productive capability. We're going to consider certain frequently reported capability measures, including CP and CPK. One finds in practice that when there are discussions on capability measures, certainly in my case, I find that CP and CPK are the most frequently reported ones. But also we're going to talk about the Sigma capability estimate. Of course, in the Six Sigma methodology, one is typically required to report the capability, or at least estimate of the process capability, both before and after a project has been completed. And one finds in such cases that the so-called Sigma capability estimate is required. So we're going to talk about that, but actually deal with it in much more detail in one of the later modules. Let's state the assumptions that we should be looking for in order to perform valid capability analyses. In that regard, I also want to discuss the concept of three particular types of statistical studies: descriptive, enumerative, and analytic studies. And I want to show you how these relate to capability analyses. We're also going to address the different types of data that one may be considering when performing a capability study. And finally, we're going to state some of the probability distributions that may be useful for modeling a process. So what are process capability studies? Well, in essence, going to the very core of the argument, these are investigations where we're trying to assess the ability of a given process to meet certain requirements, or we're going to call them specifications. Now, for capability studies that are going to be addressed in this presentation, I'm going to regard a situation where there are both upper and lower specification limits. Now, we mustn't confuse these with, let's say, control chart limits. Of course, control chart limits are based on estimates of variation from the given process itself. Specification limits are typically derived by the engineers or the voice of the customer. Let's put it this way. We are trying to give ourselves a particular interval such that if we are falling in this area indicated by the green arrow, then we will say that the, let's say, the particular unit that we are considering has passed. It is acceptable. It is within the specification limit. If, however, what we are observing is providing a measurement that falls outside of these specification limits, either below the lower specification limit indicated with the red arrow on the left-hand side, or if it falls above the upper specification limit, of course the red arrow on the right-hand side, then we will say that we are not meeting specifications. So regarding examples of process capability, the situation that we're seeing here with this particular histogram showing a set of results, we can see that this distribution is centered and it's well within the specification limit. This is an ideal situation. We're falling slap bang in the middle. I am making the assumption here that my goal is to be centered midway between the specification limits. And one finds in practice that that is quite a useful characteristic that we'll want to have, falling slap bang in the middle of these spec limits. And that clearly is the case here with this particular process. I can't see any observations that are falling anywhere near the spec limit. In this situation, we also have the distribution falling kind of centrally between the specification limits, but you can see that there are more observations getting closer to the lower specification limit and the upper specification limit. It's indicating that for this particular process, values that we're obtaining are exhibiting a higher degree of variation. Okay, so it's not as good as it was before. Yes, they are all falling snug inside the specification limit, but it's not as capable a system as we saw in the previous example. Clearly, this is not a good process with regard to the specification limit. It's got very poor capability. It's centered not midway between the specification limits. Again, I am assuming that that would be my goal in this case. Instead, I can see that there's an awfully high proportion of this distribution that's going to be falling below the lower specification limit. So you can see the danger of having a distribution that is centered, let's say, on a particular side away from the center of the distribution, with this kind of bell-shaped curve that we're seeing here for this particular distribution. It incurs a higher proportion of values that are going to be falling, in this case below the specification limit. That's poor capability. Another situation where we're seeing poor capability, okay, the process is centered midway between these specification limits approximately, but there's such a high degree of variation that I've got a fair amount of values falling both below the lower specification limit and above the upper specification limit. So, as you can see, that if the level of variation is somewhat excessive, especially in regards to the amount of the interval that we're allowed here for these specification limits, then I'm going to have a poor capability measure in this particular case. So how are process capability results typically reported? Well, there are several ways, and I'm going to take a look at some of them here. The first one, and probably the one that's the most intuitive, from a basic statistical perspective, is to regard the number of, let's say, parts per million that are non-conforming. Okay, so if there are 1 million observations that we have, and 500,000 of them are non-conforming, then I've got 500,000 parts per million non-conforming. Of course, that would be a 50% defect rate. That's not very good. Typically, one finds that CP and CPK values are also reported. Now, this is an area that we're going to be discussing in much more detail with regards to normally distributed data. As you'll see, that if the assumption of normality is violated even slightly, then these values that we obtain for CP and CPK can be seriously disingenuous. So in the section where we deal with normally distributed data, we're going to be dealing with CP and CPK values in great detail. And I find that these are probably the ones that are most popular out there. P sub P and PPK. All right, what's the relationship between P sub P and CP, PPK and CPK? It's all about the amount of variation that we're considering. Now, I'm purposefully going to be kind of, let's say, assuaging the importance of P sub P and PPK, because as I'm going to be discussing shortly, we're going to be taking the perspective here of performing a process capability analysis, and the process itself will be in statistical control. And as we'll discuss later, if the process is relatively stable, then the amount of variation that we see, this so-called short-term variation, as some people call it, which is just due to the common causes of variation, will be pretty darn close to what we would get if the process is stable, whether you're either computing the short-term variation or the so-called long-term variation, because the process is stable. So in that regard, the estimates that we get for C sub P and P sub P should be very close to each other, and in the same manner, the estimate for CPK and the estimate for PPK should be very close to each other as well. So this is the only situation where I'm really going to be talking about P sub P and PPK, and we'll be illustrating the way in which the results will be very, very similar to each other in just a short while. The so-called sigma value course, this is typically reported as part of the completion of a Six Sigma process improvement initiative. Of course, both before and after the project, one has to have an estimate of the capability of the system. Typically, one shows at the start of the project that the capability of the system is very, very poor, which is precisely why the project should be initiated. And then hopefully upon completion, we can show that the process has improved a markedly high amount, hence the actual initiation and completion of the project was a very worthwhile venture. Benchmark Z, now this is really considering the let's say, parts per million non-conforming and how many standard deviations away from the mean in a normal distribution you would have to be such that you get this benchmark Z value. It's a unitless dimension, just like CP and CPK, and a sigma value as well. And it is directly related to this sigma capability estimate, and we'll go into that in much more detail in one of the later modules. And something that I think is very important and is kind of underplayed out there, confidence intervals for a particular parameter. Now, we're going to be discussing in immediate terms confidence intervals for both CP and CPK, and confidence intervals for many other capability metrics as well. The crucial thing is that depending upon the type of data and who it is that you're going to be reporting these capability results to, you may prefer one type of reporting device over another. Let's say, for example, if the audience is relatively familiar with the Six Sigma methodology, then you may want to just report this Sigma capability estimate. If the audience is of a more engineering background, let's say, I would hazard a guess that they would be more familiar with CP and CPK estimates. So, you know, it's, there's no one particular reporting device that is the best one can choose. It's always good to use your best judgment in this regard. So what are the assumptions that we're going to require for valid capability analyses? Well, the crucial one, in my opinion, is that the process has got to be in statistical control. By that, I mean that the control charting device that you're using to monitor the particular process should exhibit stability. It should be in statistical control. Secondly, I'm going to assume that a particular probability distribution can be usefully employed for this process. What do I mean by this? Well, we're going to assume that the underlying distribution may follow perhaps a normal distribution if we're playing around with continuous data. Maybe not. Maybe it's another distribution that might be appropriate. If we're using attribute data and we're using, let's say, defect rates, then maybe the binomial distribution would be an appropriate probability distribution. The way in which we can investigate this will be discussed in due course, of course. Now let's note that if the process is not in statistical control, we cannot obtain reliable estimates of, let's say, the process mean, of course, the process standard deviation as well. If your R chart is out of statistical control and you're using, let's say, R bar over D2 to estimate the process standard deviation, if it's all over the place in your R chart, then, of course, the process standard deviation is not stable. Hence, any kind of capability estimate that's derived from it would be questionable, to say the least. Now, when calculating capability estimates using so-called long-term data, now this includes periods of time when the process is out of statistical control, we typically obtain estimates of the standard deviation that are larger than would be the case in the short term. What's the situation in which you may see this? Well, let's say that you're going to be doing some kind of a quality improvement initiative, and you need to be able to provide an estimate of how well, or I should say how badly, the process is actually performing. In that regard, you probably have access to a fair amount of historic data. So you may be tempted to use like a big old standard deviation for all of these particular data points. If you do that, then of course this so-called long-term data may well be including periods of time where the process was all over the place, out of statistical control. If the process is not stable, then I can't really put my hand on my by heart and say, this is what I expect the process to give me for when it is stable. So to compensate, what is sometimes done to estimate this short-term capability, that is when the process would be in statistical control, sometimes there's a compensating element that's added into the calculation, this so-called long-term sigma shift and drift. You take the sigma value and you add 1.5. We're going to be discussing that, of course, in much more detail later on. It is a controversial topic, I'll say that. I'm going to kind of assuage it as far as the materials that we're going to be discussing here, because I'm going to be making the assumption that the process itself is in statistical control. But I'm not going to sidetrack this. I will discuss this in much more detail in Module 4. So let's explore this a little bit further. Why does the process need to be in statistical control? Why am I so vehement in my requirement for this? Well, as I just discussed, a stable process, that is one that's in statistical control, will provide meaningful estimates of particular process characteristics. Let's say, for example, the process mean and process standard deviation. That's going to be very important if we're assuming that the distribution is, let's say, it follows a normal or a Gaussian distribution. However, to fully comprehend the importance of stability in the context of performing a capability study, it's important to consider three particular types of statistical studies. There are descriptive studies, there are iterative studies, and also what we call analytic studies. We're going to explore each of these in turn by way of an example. So here is the scenario that we're going to be considering. There's a quality practitioner, and they're required to estimate the proportion of glass vials in a shipment that's failed to meet certain manufacturing specification limits. Okay, so think about it this way. We need a particular vial to fall inside certain limits. In the first case, I'm going to say that if all vials are for a shipment to a one-off customer, okay, we're just going to be sending it to this particular customer, it's a one-shot deal, and all of these vials are going to be individually assessed, then this is what we call a descriptive study. Okay, so it's just a one-shot deal, everything's going to be measured. Therefore, there is no wider inference that has to be made, and the entire population is going to be addressed. This resulting proportion, therefore, is the population proportion. It's a parameter. It's not a statistic. We're not estimating what the true proportion is going to be. We have calculated the true proportion because our entire population is being assessed. So if we try to use, let's say, hypothesis tests, we're going to do like a test for one proportion. We're going to do a confidence interval for one proportion. Well, if you try and do that under this particular case, then this would be an invalid scientific method. Utterly inappropriate because we have the answer. That's what we get when we're performing one of these so-called descriptive studies. Now let's deal with the same scenario again. We're looking at these glass vials. But for this particular case, case 2, I'm going to say that all of these vials are for a shipment to a one-off customer. Okay, so just one person that we're going to be sending it to, let's say one particular organization. But in this particular case, not all vials can be assessed. However, we can take a smaller representative sample that can be obtained for evaluation. Now, in that particular situation, the study that's being performed is called an enumerative study. The resulting proportion that we obtain from this smaller representative sample is therefore an estimate of the population proportion. It is a statistic. So in this particular case, if we wanted to perform hypothesis tests, let's test whether the true proportion is equal to, 5% or whatever it is that we want to consider, then that would be an okay thing to do. If you wanted to obtain let's say a 95% confidence interval for the true proportion within that So again, we've got this quality practitioner with the glass vials, but for this third case, we're going to say that if the vials are being continually manufactured, okay, it's an ongoing process. We're making these vials day in, day out, and we're shipping them to customers all over the place, and we're concerned with the manufacturing process itself, then these measured vials, whether I do 100% inspection or not, are merely a subgroup of an infinite population. Okay, so even if you're going to be sending it to, vendor A, and they're checking all of them, you might be saying to yourself, well, hang on, that's a descriptive study. No, it's not, because the population itself is technically infinite. What we've shipped to them is a smaller representative sample of everything that we're going to be manufacturing. This resulting proportion is an estimate of the true proportion that this process can deliver to our customers. So for our estimates of process capability to be valid, this particular process needs to exhibit stability. If we want to use enumerative study characteristics, like, let's say, confidence intervals for process capability indices, it's only valid for us to use these enumerative-based statistical tools for an analytic system if this particular process itself is in statistical control. Now, these three cases here, this kind of discussion of descriptive, enumerative, and analytic studies, this is based on I don't know if it was originated by W. Edward Deming, but that's certainly where I learned it from in his book on survey sampling techniques. And I think that it's kind of rooted in many discussions, but especially for capability analysis, and this can solve a lot of arguments when people say, should we be using confidence intervals? Should we be assessing the capability and just saying that this is the true value? I am going to be making the assumption from here on in that it's this case, case 3, that we are considering for our analyses. So what are the types of data that we're going to be considering for our capability studies? Well, continuous data, also called variables data. Let's say if we're monitoring the amount of time that it takes, then it could be time in minutes or days, something like that. It could be measuring something and we're looking in terms of inches or millimeters or kilograms or pounds, depending upon what kind of a scale it is that you want to employ. Categorical data. We're able to put data into particular categories. Let's say that we're going to be considering nominal data. It's just like a particular grouping. It could be particular colors, or it could be particular days of the week, something like that. Nominal data, we're just putting it into particular categories. Binary data, let's say pass or fail, on time or wasn't on time, something like that. That would be a binary response. Now, depending upon the type of data that is under investigation, a particular type of probability distribution may be used to model that process. For continuous data, pretty much the default that people look to first is, does a normal distribution adequately fit this particular process? Sometimes it will, sometimes it won't. It depends. If it doesn't, then it would be appropriate for us perhaps to consider other distributions, for example, the Weibull distribution or the gamma distribution. Of course, all of this is going to be discussed in the detail in the module that is assessing non-normal data. For categorical data, it may be appropriate for us to model it using distributions like the binomial distribution or the Poisson distribution. And again, we'll be addressing that in a later module. So in summary, what have we addressed? Well, we've defined the concepts of process capability analyses. We've looked at some examples for what would constitute both good and poor processes in relation to their capability. We've listed and kind of discussed in general terms certain frequently reported capability measures, including CP, CPK, and the sigma capability estimate. We've assumptions for performing valid capability analyses. We've discussed the concept of descriptive, enumerative, and analytic studies, and in particular how they relate to our interpretation for capability analyses. We've discussed the types of data that one may want to consider when performing a capability study. And finally, we stated, but we haven't explored in any detail, some of the probability